as constant entropy, constant volume, constant entropy, and constant volume, and he came up with this. So this is just a simplified model for the actual cycle. This is all what has been done. So this is here the PV diagram and TS diagram, and it's your responsibility to learn what happens in the first process. It is isentropic process. So once we say ideal cycle, ideal standard air standard auto cycle, then you know these diagrams. خلاص, that's it. Okay, then process 1 to 2, 2 to 3 is heat addition, 3 to 4 is expansion, isotropic expansions, then 4 to 1 is exhaust, constant volume exhaust. Then we went to an example, and I was quick in that, but I asked you about the compression ratio. And can I hear from you what the compression ratio you found? Say the name and the type of engine.
Yes, Faisal Al
Okay, Faisal.
diesel engines from 14 up to 25.
Okay, remember this, Shabab. Diesel is 14 to 20 something. Okay, anyone else?
Yes, حسن السهاتي.
أهلا حسن.
Fuel combustion about 10 to 14.
Okay, this is gasoline engine. Okay, this is gasoline, not diesel. So now Hassan gave us 10 for gasoline, and Faisal gives us more than 14 for diesel. So it is a fact now. I'm sure that all of you agree to that the gasoline engine R is around 10 or so. The diesel engine is more than that. It goes to 15, 16, and more than that. So the compression ratio in diesel engine is much more than in gasoline engine. Gasoline engine are the spark ignition engine, and diesel are the compression ignition. So we can say that the compression ignition engine R is more than 14, as Faisal gave us, and for the spark ignition engine, about 10, as Hassan gave us. I'm sure that all of you agree to that. Okay. Remember this very important fact here. I wanted to know that. Then we went here with the analysis. So this is your second thing that you should know is how to analyze that, because this is a system here. So we say here W12 is this isotropic, so Q is 0, so it remains as U2 minus U1. Remember, we are using U here because this is a closed system. Then 3 to 4, this is the expansion. The work expansion is also isentropic, so there is no heat, so U3 minus U4. Then we have 2 to 3, there is no work done here, so it is Q is equal to 3 minus U2. So this is Qn. Then Q out is U4 minus U1, also because there is no work done here. So this is your second point to know here the analysis. In addition to that, you write eta here is 1 minus QL over QH, and this will give you here the efficiency. So this is one of the things that, the second thing that you should know about that. Okay. Then we went to an example. We have seen that this is the heat addition and the work done. We have covered this. So let me go to the example, because this is what we have last time, but I went quick through it, and I asked you to go and read this example or any similar example for auto cycle. Okay, now what we need, the question is that calculate W net, calculate the eta thermal. So this is what we need to calculate here. The work done, the net work, eta thermal, and also some others there, back work ratio and mean effective pressure. So this will be always a question like that, no more than that. The main two things here, efficiency and network. In addition to that, we ask for back work ratio, which is the compressor work over the turbine work. This is what we give, and this is what we take, and therefore we need to know how much the compressor will take from the work of the turbine. And then the mean effective pressure, as we have defined last time, it is W net, this area, over V delta V from A to B or from 1 to 2. We will see the analysis for that. So what I need to know here is, this is the question here. All the time, this is what we need. What is given here, we have 4 processes. Therefore, if I want to plot this cycle here, I need P1 and T1 here. And all the time, P1 and T1, this is coming from atmosphere. This is at the at the inlet to the internal combustion engine, and this normally comes from atmosphere, and therefore this is normally atmospheric condition, 100 kilopascal, 300 Kelvin, or something like that. If it is not given the problem, you will take it atmospheric condition. Then, so this state is well defined now. Then I can go, I know the direction now, it is isentropic, but then it has to give me something here to stop. It gives me the compression ratio. Why compression ratio? Because now you went to the internet and you get it. So it is available once you buy the engine, you know what is the compression ratio. So we can reach state 2. So now we have 1, 2, and then another, the compression ratio 3. So 3 pieces of data. Then heat addition, and then we have to stop at somewhere here, maximum temperature or maximum pressure or whatever, and therefore this is the fourth piece of data. With this here, I can plot the cycle. So I need 4 pieces of data. All the time I need 4 pieces of data. So it says the Otto cycle having compression ratio. So this is given 9 here. As Faisal gave us, it was mentioned 10.2 or something. So this is normally something like that. This is for Otto cycle. It's always something like that. But Otto cycle will never have 15 compression ratio, because the next cycle will do that. So it uses air as the working fluid initial. So it's giving us P1 and T1 here. All right. And it's giving us the total volume. Total volume, this is not a property, but it just decides here what is the size of the engine. And therefore, this is the volume at state 1 here. And we use it to calculate the mass inside the cylinder. It says during the heat addition, we have 7.5 heat addition here. So now it give us here the heat addition in this process here. So now I have 1, 2, 3, and 4. 1 is the compression ratio, P1 and T1, and then it's the heat addition, this kilojoule per kilogram here. This kilojoule is the total. I use this here and this one because this is kilojoule. If I divide this by this one here, it will give me kilojoule per kilogram. And therefore, the first one I can get from here as kilojoule per kilogram. So now I need 4 pieces of data. So the process to do is this. All the time, this is systematic process to do. You have to get all the temperatures here. And once you get the temperatures, then you can get the internal energy, the values for you here. So this is what you need to do here. Let me just go back to this one here. You need to calculate the values for U1, U2, U3, U4. Once you get all of this here, then you can finalize and get the efficiency. And therefore, to get the internal energy, it's a function of temperature for ideal gas. So I have to get the temperatures. All right, so this is what I have. Okay, so now I go here to the problem. So we get to 2. How do we get to 2? We have this relation for isentropic. We have PV to the K equal to constant, and we have PV equals to RT, and therefore in thermodynamics 1 we get this here. T2 over T1 is equal to V1 over V2 to the K minus 1. This is because it is an isentropic. K here is CP over CV. So given CV is that, CP is 1, 1 over CV will give me 1.4. So K here is given. I have V1 over V2. What's V1 over V2? This is the completion ratio is given to us here. So V1 over V2 is 9, and then T1 is around 100 kilopascal, and then I have T1 is given. Remember, this has to be in Kelvin. Okay. Then we have this, we can get T2. So now I have T1, and I can get T2 as this. Remember that T2 has to be greater than T1. If you reverse this, you will get T2 less, and therefore this is not acceptable. So T1 is the minimum, T3 is the max. So you get T2 here. Any question about getting T2, Shabab? Shabab?
No, clear.
Okay, so we need to calculate, this is the process here. You have to calculate T1, T2, T3, T4. So now we have T1 is given, and this will be normal. Even if I don't give you that, assume it is atmospheric condition. From 1, we can get to 2. Then, if you want P2, you can also apply the equation here, that this is isentropic, PV to the K equal to constant, so you can get the pressure here. But it's normally not required. If you want to calculate the enthalpy only, this will not be required, but you can do this here. Now I want to move from 2 to 3. So he's giving me Q here as 15 kilojoule. So, but I need kilojoule per kilogram because I'm working in kilojoule per kilogram. And therefore, we apply this equation here, Qn is equal to mCV T3 minus T2. If I divide by the mass here, so this will be CVT3 minus T2. In most of problems, he gives me T3. But in this problem, he gives me Q. So either he gives you Q or he gives you the temperature at 3. Anyway, he's giving us Q here, so I need T3. So I need to calculate the mass first. And he has given me the volume, total volume. So I get the specific volume, RT1 over P1 at state 1. So this will be specific volume here. From this, I go in now and this is given 7.5 kilojoule. I divide by the mass, and the mass will be equal V1 over specific volume. V1 is given is 3.8, and then specific volume V1 we calculated from RT over P. So now we can get Qn. Qn is the heat added from 2 to 3 in kilojoule per kilogram. Now I can apply this equation and get T3. As I mentioned earlier, in most of our problems, we will be given and then calculate Qn. But this does not matter here. If it gives you Qn, you can calculate it anyway. So I have 1, 2, and 3 calculated. Then it remains to calculate T4. So go if you have any question, please stop me at any time. Then we can go to 3 to 4. Of course, I can get here P3 as well because this is constant temperature, constant volume. So I say that P over P is equal to T over T. This comes from PV equals RT for state 2. PV equals RT for state 3. Dividing, the volume will be cancelled. Therefore, P over P would be equal to T over T. So I can get P3 if required. In this problem, it is required. But in general, to calculate the efficiency and network, I do not have to calculate the pressure. Then I get T4. How can I get T4? This is isentropic. So I apply the isentropic relation that T4 over T3 is equal to the volume ratio K minus 1. The volume ratio here is the same as R. Why? Because V3 is equal to V2. V4 is equal to V1. Therefore, this ratio is equal to V2 over V1, which is 1 over R. So now I can get T4 here. Remember also that T2 and T4 are greater than T1 and less than T3. It has to be like that. Don't make mistakes. The mistakes comes if you use this R or 1 over R. So if you use this R, you will get this 2,000, 3,000, something like that. So remember here that T1 is the minimum, T3 is the max. So now we got T4. If you want to calculate also T4 from this relation here. So now we have T1, T2, T3, T4. So this is almost, we have solved most of the problem now. Once we get the temperatures, then خلاص, we can calculate Qn. Qn is given. If it is not given, I can calculate from T3 minus T4. Then I calculate Q out is CV T4 minus T1, which is U4 minus U1, the previous slide. So now I have CV, then I can get Q out now. And I know Qn, so I can calculate W net is Q in minus Q out. I can get the network here. Once I get the network, then I can go calculate the efficiency, W net over Qn, and this will give me the efficiency of Otto cycle. This is the most important. Every question will be like that. Calculate the efficiency, and this is the way. So you calculate all the temperatures, and then use delta U as CV delta T, and then you calculate the efficiency. I have some notes to say about the values here, but I will come back to that. The mean effective pressure is defined as this. V W net over V maximum, which is V1 minus V minimum, which is V2. Then I can take here, I say W net over V1 minus V2, which is this one here. The V1, if I take V1 out, then V1 minus V2 over V1. V2 over V1 is 1 over R. So now with this here, V1, we have calculated that. So I can get the mean effective pressure at this one. Now the back work ratio is W compressor over W turbine. So I divide W compressor, which is delta U12 over delta U34, and this will give me 22.5%. Okay. Now I want to say some comments here. The first comment that I will ask Yazid back.
Yes, I'm here, Doctor.
Okay, welcome back. Okay. Alhamdulillah, you are okay now. And I will ask, I think it was Faisal, I believe. I wanted the back work ratio. You remember I asked you in 3 weeks to remember something, which is vapor power cycles. What is W pump over W turbine? What was that?
The pump work was 6 point something kilowatt.
And W net?
W net, I think in the 500 something like.
No, I think it was 1,000 also. But anyway, I accept 500. Okay, but it was 1,000. So the idea there is that 6 over 1,000 is very small, right? So the pump takes very small work with respect to the turbine. This is in the previous chapter. But now in this chapter here, the compression process takes 22%, let us say 25% approximately of the turbine work. Remember this because I will ask you again in another week. Next week, I will ask the same question again. So now for vapor power cycle, W compression is very small. In gas and internal combustion engine, the compressor work takes 22.5, or let us say 25%, 1/4 of the work. So this is too high now because this is a compression of a gas. When you compress a gas, it takes more work than compressing liquid. So this is the first note I wanted to mention here. Also, look at the efficiency here. The efficiency is 58%. I want to ask you, in the internal combustion engine, what's the efficiency? The actual one. Can you give me a number? Is it more than that or less than that?
It's less, doctor.
Less
It's
than
about
that.
38, I believe.
Okay, it's about 30 something. So this is about 30 something. This is the efficiency of the actual engine. But why we are getting high values here? Because we are considering here that this is isentropic. This is isentropic. When we have no combustion, we have no gases out of the cylinder. So because this is ideal here, therefore this is high a little bit. But when we consider actual cycle, not reversible, there's heat losses, all of that, then this will come to be 30%. But I want you to remember the 30%. When you go to engineering, alas, remember, keep this number 30%. But when the office, this is simplified, so you know it will be a little bit more than that. Okay. So this is here solving the problem. Any question here solving the problem? So all what you should do, when I say auto cycle, then you have to know this, memorize it or whatever. Anyway, in our exams here for the pandemic period here, you have this at home, so you can copy it. But I want you to know it. Okay, it's one of the things that you should know. What's auto cycle? The second thing, once you know this, then you go to the analysis. How do you calculate WN? How do you calculate W out? How do you calculate heat addition and heat rejection? Then how do you calculate the temperatures? And then how you come up with these answers here. This is all your responsibility in that. I don't intend to complicate it more than that, but in some cases, you may give an efficiency here for the turbine, you may be given efficiency for the compressor. And of course, you know how to do that, and therefore you can use 3 and 4 prime and 1 and 2 prime. This is similar to what we have done in the previous case. But in here in this chapter, you can always work as considering ideal gas situation. Any question here before I go to the next cycle? Shabab? So what's your responsibility today now? What should you do today? Okay, not tomorrow, today. Is you go and solve one problem at least, or solve this problem or another similar problem from the book, or even the example in the textbook, and solve it yourself and see if you get all the answers correct or not. Okay. With this here, I move to the second cycle here. Are you with me, Shabab? Shabab?
Yes.
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 Okay. So let me go to now the second, but let me just go to the next slide here first, and then I come back to this one. Okay. This is here, remember this is the actual cycle for diesel, for gasoline engine, for spark ignition engine. And therefore, Otto cycle found that he can approximate this as a vertical, and this as a vertical, and those are isentropic. Now, diesel, another scientist, went to the actual cycle of a diesel engine. And this is not the one here, but he found that this is close to be horizontal here. He found that this does not go like that, but it is horizontal. And therefore, he said, I will go here for this process and approximate it as a horizontal line here. So it is just an approximation here. He found that it is better to make this as close as constant constant pressure, and therefore he divides this one here. So this is the only change here in diesel engine. It is likely that this is constant pressure, not constant volume. So it is just a simplifying of the actual cycle. Okay, now let us go to this now again. Okay, so now we are introducing what's called air standard diesel cycle. This will go to the compression ignition engine, which is the Faisal car now. Faisal bought a car which is diesel engine. He found that R is 14 to 20 something. And now we are going to consider his engine and consider approximation for this engine. And approximation here, it is air standard. Air standard we mentioned before that we consider the ideal cycle. We consider that there is no inlet and exhaust, it's fixed mass, and there's a heat addition, not fuel combustion. All of these conditions here, assumptions we made here. And therefore, we came up with this one. So the difference between auto cycle be 1, 2, and this is vertical and expansion. In this cycle here, this is horizontal like this. Why we make it horizontal? It's just to fit the actual performance of the engine, the actual process of the diesel engine. All right, so now we have, first of all, from 1 to 2 is isentropic, as we have in the auto cycle. So when you have 1 and 2, it is the same as auto cycle. All the difference here is that what we reach today, that R will not be 9. R will be around 16 or 17 or 18, something like that, because this is a diesel engine. So this is isentropic compression here, 1 to 2. Then we have constant pressure heat addition. So the heat addition here is at constant pressure. This is the only difference from the auto cycle. Then we have isentropic expansion in the turbine. This is similar to the turbine. Then we have the last process is constant volume heat rejection from 4 to 1. So this is what we call diesel cycle. And I can tell you should know now of how to proceed with this cycle. Now the next step is to make cycle analysis. What cycle analysis? To calculate W compressor, W compression, to calculate heat addition, to calculate W expansion, to calculate QL, and then get W net, and then get the efficiency. It is the same procedure. All right, it's the same procedure. The only thing is this process here. So now let us go to cycle analysis now. Okay. Cycle analysis, we have we will define. We have diesel compression. R is equal to V over V2, similar to the auto cycle. But now R is large now. It is more than 14 for the previous cycle. It is around 10 or something like that, between 9 and 11. Okay. The second thing is that we need to define here V3 over V2. I need to define this volume here. So this 1, 2, and 3. What is V2 and 3? All right. Forget about combustion initiated here, but this is like a diesel engine. Combustion initiated here is not spark. It happens here that we inject the fuel. So we start injection the fuel here at this point. So in the diesel engine, as we have seen in the videos, you sent a lot of videos, and I hope that you looked at these videos. You do that. I spent a lot of time reading your videos, and it was very useful. And I hope that everyone, not just copy and the link and send it to me. I need you to look at this. So what happens here is that we have in the diesel engine, we do not have a spark, but what we do is that we compress this here. At this point 2 here, we have high temperature, we have air and high temperature only. And they are waiting for the fuel. So here we inject the fuel. So at this point, we start injection the fuel, and then at this point, we end the injection of the fuel. So we start injection of the fuel here. Let me say again that in this diesel engine, we have only air inside now. We do not mix the fuel, we do not add fuel. So I compress the air and then compress it higher than the self-ignition temp. So at this point, I have air and temperature is high. So what's waiting for is waiting for the fuel. So we start injection the fuel here, inject the fuel until at the end here we close the injection. And therefore they will call it cut off injection. So start injection here, and here we cut off the fuel. So we stop fuel injections, therefore we say cutoff. And therefore we have a ratio here. This ratio is V3 over V2, the volume at 3 divided by the volume at 2. And therefore we call it cut-off ratio. Why is cut-off ratio? What does this mean? It is cutting the fuel here. So we start the fuel injection and then stop the fuel or cut the fuel. This is why we call it V3 over V2. So this is another parameter, and sometimes, not all the times, it is less important than that, but you may find it here in the diesel engine. So this is the cut-off ratio. All right. Then we need here to analyze now. We need to analyze the cycle. So what do we need from this analysis to get the efficiency? How to get the efficiency? I have to get 1 minus QL over QH. And then this will give me the efficiency. The network is equal to QN minus QW. So QL. QH minus QL, or W turbine minus W compressor. So let us do the analysis now. From 1 to 2, we have already treated this in the previous part. It is U2 minus U1 because this is isentropic, Q is 0. So this is done, خلاص. Also the same for this one here. Same for W turbine here is CV T3 minus T4. And then for the QL, it is CV T4 minus T1. Now it is only, this is the difference here. So you do with 1 and 2 similar to the Otto cycle. From 3 to 4, similar to the Otto cycle. From 4 to 1, similar to the Otto cycle. So you just repeat what we mentioned there. It's only this point here. This was constant volume, now it is constant pressure. How we deal with that? So what I do here is to apply the first law for this process. Now let us apply this. Q is equal to delta U plus the work done. Okay, Q is equal to delta U plus the work. In Otto cycle, the work was 0 because it was vertical. Here, the work is not 0. So the work is P V3 minus V2. So this is the difference here from Otto cycle. Otto cycle, this was 0 because this was vertical. Now the work is P V3 minus V2. Then we add U3 to this and add U2 to this. Then it comes to be H3 minus H2. So now I have here, this is H3 minus H. So Qn is H3 minus H2, not U3 minus U2, similar in the Otto cycle. So this is the only difference here. And therefore, you can get U4 minus U1, which is from previous, similar to the previous cycle. But when you divide here, you divide over H3. So Qn is H3 minus H2. And therefore, you can calculate the efficiency for this cycle. Shabab, do you want me to repeat anything? I can.
Yes, Doctor, can repeat it.
Sure, I will do that. Thank you. Is there any comments on the WhatsApp from students that anyone has not able to join or? Okay, I think they solved that. Okay, so now let me say here that okay, let me go here again. Let me just go to the previous cycle. Okay, in this cycle here, this is the Otto cycle. Okay, I'm just telling you the Otto cycle. Otto cycle was 1 to 2, 2 to 3. This was vertical, mean isentropic process. This is constant volume process. Then from 3 to 4 isentropic and so on. What we are going to do from the change from this cycle is that instead of 2 to 3 in the diesel cycle now, instead of 2 to 3 constant volume, 2 to 3 will be constant pressure. That's the only change here. Okay, so constant, this is constant volume, this is constant pressure, this will be diesel cycle. So if I go from Otto cycle to diesel cycle, then I'm going to change this vertical line to horizontal line. Therefore, what I'm saying is the calculation from 4 to 1 is the same as this. 1 to 2 is the same. 3 to 4 is the same here. The only change is from 2 to 3. And this is what we are going to do in the next cycle here. So now let us go to the same slide here, which we are repeating. Okay. So I'm going only to talk about this process here. Why? Because this will deal with it similar exactly to the Otto cycle. This for Otto cycle, this same as Otto cycle. Here in this cycle, now let us go back to thermodynamics 1 and apply the energy equation. Energy equation for a closed system says that Q is equal to delta U plus the work done. I need to hear okay from the one who said repeat.
Yes, okay.
Okay, so always every part I will stop until you tell me okay. So now we say that this is the energy equation applied to a system. Q is equal to delta U plus the work done. In the previous cycle, this was vertical. So integral of PDV was 0 previously. Now integral of PDV is not 0 here. It is P2 V3 minus V2. So we have work here. So now I say here that the work is PV3 minus V2. So now we come up with this here. Is that okay?
Yes.
Okay. Now what I'm going to do is that add this U3 to PV3. U plus PV is equal to enthalpy. So I'm going to add this to that. It comes to be this part. I add U2 plus PV minus plus this term, which will come a negative. So this will give me that. This term, we'll call it H3, and this term, we'll call it H2. So the case here is that Q is equal to delta H or H3 minus H2. Okay?
Yeah, now it's clear.
Okay, very good. Then when we calculate eta here, U4 minus U1, we calculate it as the same before. This is like auto cycle. But here, this is the only difference here. The difference is that Qn is equal to delta H, then I calculate eta. So now you can go to any problem for diesel cycle, and then you calculate it easily, following the same as auto cycle. Only when you come from 2 to 3, you apply delta H rather than delta U. This is the only change. I can resolve the problem previously we solved it, but when I come to calculate Qn, I just replace U, delta U by delta H. That's only thing that we have to change. All right, Shabab?
All right, thank you, Doctor.
Okay, so let us go to yes question. No question. Okay, then let me go now to, so this is air standard diesel cycle. This is the heat addition now. Okay, this is for 2 to 3. This is 1, 2, 3 on the okay, and the TS diagram. It is the area under 2 to 3. This is the heat addition. So this is the heat addition, which is all of this area here. Then we have this is the heat rejection, and therefore the area enclosed here, this will be the network done. All right. It's giving us here the work done also. So this is on the PV diagram, the work is the area under this, and this is here, this area here, and this is the work done by this one. I want to ask one question here. You look at this area here. Okay, you see this area. How much percent from this area?
40, 30, something like that.
I'm looking here, let me look at this again. This is the area under this curve, and this is the area under this curve. What is the ratio here? I mean, what is the, if I divide this area by this area, what's the value?
25.
Very good, 25. Thank you. I just mentioned just 5 minutes ago. So this is the back work ratio. It is the work done by the work needed for the completion, and this is the work given by the expansion. So this is 25 here. If I just simulate this here by the previous cycle, vapor power cycle, this will be negligible with respect to this area for the previous shot. But now it is 25. I will repeat this question again. In next week, I will ask you what is the ratio here for the next cycle. And this will be different from this one. Okay, so now when we do that, so this is subtraction of these two here. This will give me the network of the diesel cycle. All right, Shabab, any question in the diesel cycle now? What should you do at home? Go solve any example. I'm not asking you to solve. Go to any book and get an example, even the internet, get an example and solve it yourself and compare your results with the solution. All right. Now I want you to go to deep thinking a little bit here. Okay, before I go to the next cycle. Okay, anyone is ready, has a good breakfast, has a cup of tea, cup of coffee, and ready to go in deep thinking here. All right, Shabab. Can you wake up? Okay, wake up,
Yes.
and I want to think with me here. I'm going to give you an assignment at the end of this here. I want to compare between diesel cycle and auto cycle. Okay, as we have seen in the previous part that the compression ratio will give you higher efficiency as R increase when you go and buy gasoline engine, the one as not Faisal Hassan went, he got a gasoline engine and he said that R is 10 point something. Now, when you look at this number here, try to look at another engine and get higher compression ratio. As the engine is higher compression ratio, then the efficiency is improved. Okay, this is for the gasoline engine, not for the diesel engine. I want to repeat some physics about this here, and then I want to talk about comparison here. So let us talk about this is here is Otto cycle, and superimposed on it is diesel cycle. Do you agree with Matt? So 1, 2, 3, 4, this is Otto cycle. 1, 2, 3, D4 is diesel cycle. I'm superimposing the two cycles on the same figure. I want someone to say, okay, every while. Okay, Shabab?
Okay.
You know
Yes, okay.
superimposing. And superimposing, this is Otto cycle. I'm putting a note here, diesel cycle. And I want to check your understanding now. For the Otto cycle, during this process, what do we have, fuel and air or air only on Otto cycle?
Fuel and air.
Fuel and air.
Very good. So in the spark ignition engine, we add fuel and air here. And why does it not burn? Why does not burn here during the compression?
Because the pressure not reach the
The
self-ignition.
pressure.
Because the self-ignition temperature is not high. When you go to the gas station, they give you a warning. Do not use any spark. Do not use the mobile. Do not have a spark. Why is that? Because they are worried about firing. But you still do this and smoke. Nothing happens. Why nothing happens? Even you smell fuel and air. Okay. So I need three things here. I need fuel and air, and I need to have this at higher temperature. So at this point here, from 1 to 2, I did not reach the self-ignition temperature, and therefore it did not burn. And therefore, in an Otto cycle, this 2 here has to be less than the self-ignition temperature. How can I increase the self-ignition temperature now? I make it a spark. So now I have fuel and air plus spark, then it will burn. Okay, Shabab? Now let us move to the diesel engine. What do I have here from 1 to 2? Air or air and fuel? Air only. And then I can heat this up to self-ignition temperature or not? Will it burn
Yes.
or not? So now
Yes.
we reach here 2 higher than self-ignition temperature. Will it burn or not?
Yes.
Yes.
Yes. It will
How
burn.
come is that? You have only air?
No.
No, it will not burn because there's no fuel, right?
Yes.
Yes.
All right,
So
right.
at state 2 here, then we have air and temperature. Then we inject the fuel. When you inject the fuel, then it burns. Remember here that it has to be controlled combustion. If I inject the fuel all the time here, there will be a problem. So now let us go to, again here, why is R that Faisal found is higher than the one that Hassan found? Faisal told us that in compression ignition engine, we have R is more than 14. But Hassan told us it's 10. Why it's not more than 10? This is the point here. Look at the spark ignition engine with Otto cycle. I have fuel and air. If I compress it more, I will reach a higher temperature range than the self-ignition temperature, then it will burn. If it burns, all of the inside the engine will burn all together. Means that this will be we call detonation. This is explosion, and the engine will crack. You see my point here. That look at let us go from this point from this diagram here. I have at 1 in the Otto cycle. I have fuel and air. I keep compressing here. What happens to the temperature? Temperature increases. If I reach the self-ignition temperature, what happens? All of the inside the cylinders, all of it will have the fuel, the temperature, and therefore every part of the fuel will burn. And this will be like explosion. Okay, so this is, we do not want to do that. So we cannot increase R than around 11 or so. Otherwise, it will be explosion here. And then, so we keep that, and then we have the spark slowly, part by part, will burn, and therefore we have this is what we call combustion, not explosion. Let us look at the diesel engine. In the diesel engine, we have air only. So I can increase R here, right? As Faisal told us, I can go to 18 or 19 or 20 or more. And the temperature will be higher than self-ignition temperature. But nothing happens, no burning. Why? Because I don't have the fuel. Then I add the fuel here, and then the fuel is added, and then I have controlled combustion, and therefore this is the process here. So this explains why R is higher than the in diesel engine than in the gasoline engine. All right, Shabab. Okay, can you go and read more about this? Can I ask how many of you understood this? I do not expect that I have 31 students understand that, but if I have 5 or 10, I will be more than happy. Okay, can you say yes or no?
Yes.
Yes.
1,
Yes.
2, 3,
Yes.
4,
Yes.
5. Okay, so
Yes.
I have enough for me. This is satisfying me. Yes, if you have a question, I can answer. If you want me to repeat it, I can repeat it. Okay, but I want you to read about this. Okay, and I will ask you in some of the exams about this. Okay, now let us go to the more critical thinking here, more depths in thinking. I want to compare the two engines here. As we mentioned here, that as R increases, the efficiency is increased. But does this mean that Faisal engine is always, because he has more than 14, is always better than Hassan? That gives the efficiency more than Hassan? This is the question. So this is why I want to compare the two cycles here on certain bases here. R and QH, R, P. I want to set two parameters and compare. So I'm comparing here from 1 to 2 here. Do they have the same compression ratio or not? Look at the two engines here. Do they have the because it is V1 over V2 for both of them the same. So this is the same compression ratio. The second thing here is that do they have the same Q out or not? Look at the area under 4 to 1. Do they have same QL?
Yes.
Yes.
All right. So what is which is better efficiency now? Is it the auto cycle or the diesel cycle?
Auto cycle.
Because QL is less. Is it? What happened? What happened to the network?
Yeah, because the network in auto is higher.
The network is higher, and QL is the same. So QL is the same means that QH is the same, right? Sorry, I'm sorry. I mean that QL 1 minus QL over QH. So now we can see here, or W net over W net plus QL. QL is the same, so W net here is less in the diesel cycle. So now we can see here that auto cycle is more efficient. Auto cycle is more efficient because the network here is close. I will for auto cycle the network is more than the diesel cycle. Diesel cycle is 2, 3D, 4, 1. Auto cycle is 2, 3, 4, 1. So W net is more for the auto cycle and Q out is the same. I can ask another one here from the second law, from the irreversibility, from exergy. How can I tell that auto cycle is more efficient than diesel cycle? Faisal, can you help us in that?
Yes.
Why?
Because we add
Heat at higher temperature.
Heat at higher temperature.
Okay, so now this is one similar. If this was Carnot cycle, it's 1 minus TL over TH. TL is the same, but here TH for auto cycle is more than diesel cycle, and therefore we have this is here, the efficiency will improve. So from the first of thermodynamics, W net is more for the auto cycle, QL is the same, so it has higher efficiency. If we go to the second law of thermodynamics, then we add heat at higher temperature, means that this is more reversible, and the reversibility is this, and therefore we say that the efficiency is more. Now I want to certain assignment from you. I want you to repeat the same as we have done here, but considering constant same R, QH. same P maximum, T maximum. Same P maximum and QH. So I have 5 things here to do, and you can have more as a matter of fact, but choose 5 here. So I want every one of you to go and superimpose for the same 2 values. I have here for same R and same QL. Suppose now I go with you to the second one here. How can I plot it? If I have the same R and same QH. To have the same QH, what should I do here? I extend this a little bit more, right? To have, because the area under 2 to 3 is QH. So if I go here, I want to keep the same QH, so I go more here, right?
Yes.
All right. So now what happens here? So 3D will be a little bit to the right here. And this means that QL is more now. Okay, if this goes here up to this point, then QL will be less, will be more for the diesel engine. And therefore I can expect also that the efficiency is more. So I wanted to repeat that. If I repeat that for case 1, then this will be extended here such that I keep the heat addition the same. The area under this curve will be the same as the area under this curve. And then I calculate here, I see what is what's having more or less, and then I see what the efficiency is more or less in that. So I want you to superimpose for different cases here, and then let me know what is which one of them higher efficiency and higher network or less network. Concentrate on the efficiency. All right. Do you understand what do you want to do in the assignment? This is 31 of you have to know what they are going to do. I'm not sure that they will do it or not, but they should understand the question. My question now, do you understand the question? I have one case here, R and Q out, and then I superimpose this and analyze and show that the efficiency of Otto is better than the diesel cycle. I want you to repeat the same figures here, get the same analysis for 1 to 5. At least 1 to 5, you can do more here. Okay. Shabab, is the question clear?
Yes, clear.
Yes.
So you will send me, I will open an assignment for that. You will send me 5, in addition to this one, you add 5 slides like this. So this is one slide here. I want to repeat that and get other 5 slides, and then send me in with writing here which R Otto is higher than R diesel or less or whatever, and then send it to me. I will open an assignment so you can do that. So this will be also for some grades, and I'm going to give this in the exams as well. All right. So this is critical thinking about that. If you understand that, then you understand the physics. I think I'm going behind the time. I'm sorry for that. But this assignment is clear now. Shabab.
Yes, clear.
Okay.
Yes.
So I need this to be in just a couple of days or so. I'll ask for this by Sunday. So I'll make this Sunday. Sorry for being late. I will just take attendance. If you want to leave, you can leave. If no, you can ask me questions, whatever you want. Okay, but let me just take the attendance here. Okay. So I took the attendance now, and then you can leave or you can ask me questions as you want.
دكتور